All right, cool. Yeah, thanks for indulging in this. I'm just giving a talk basically on, well, the mathematics of the neural network. Mainly because I'm doing this for myself. Like I've been building neural networks for years now, and it can occasionally seem quite mysterious. Why does it work? And the question of why do neural networks work is a question that is sort of multi-layered. So we know how it works, right? It's just a bunch of matrix multiplications, but that doesn't explain anything. We need to go a layer up. But today's sorry. So today's thing. Today's talk is basically on sort of one level up from neural networks are just a bunch of matrix multiplications. We're going to deal with a bit of polynomials and reason on this level why do neural networks work. Right. So this is the sort of brief outline of what we're going to talk about. We're going to talk about neural networks. I think some of you, like Jessica, might not know particularly much about neural networks, so I added in a brief section on what a neural network is and how a neural network learns, and then I'll talk about mathematical functions. I'll talk about continuous functions and how to approximate and what things are. But really, what this is about, right, is about me trying to discover what neural networks are. See, part of this talk started, right, when I was writing my talk for the data engineering conference I gave about 1.5 years ago. And for that talk, I wanted to show examples of graphical language, but I ended up not using the portion that you're about to see. Now, if you heard me talk about neural networks, right, you would also hear me say something along the lines like the typical depiction of neural networks is wrong, right? And for example, this is a talk that I gave at Strange Loop about recreating AlphaGo, and I said, don't this type of graphical depiction of neural networks is not a good thing. But at the same time, my wife also pointed out that I frequently use these sorts of drawings for my own notes when I'm thinking about neural networks. So I'm being a bit of a hypocrite there, right? When I say that these sorts of representations should not be used because they sort of mislead you as to what the true neural network is. And I delved into this a bit last night in my live stream. So if you're interested, you can go check it out. I also put the link in the Slack. Yeah. Anyway, so what we're going to do is we're going to look at the mathematics on what we can learn from this sort of graphical view of neural network. So when I say graphical, I mean in a graphics format, right? So like I mentioned earlier, at the data engineering conference, I wanted to use these things. Pictures, because to show that languages can in fact be pictorial. There is a whole class of mathematics where you deal with pictures of lines and connections. It's a type of category theory, right? And having a sort of shared language to describe something new can always lead to something new and interesting. So so what I have put up here is multiple copies of the graphical representation of neural networks. Or are they? Because the one on the left, these ones, are not actually neural networks. They're a graphical representation of something called threshold gate, which is what you use to make your FPGAs in electronics. Then they're not neural networks. And so you can see why this is what I wanted to put in the data engineering conference talk, because there's an underlying commonality between these images, and these depictions are essentially some form of matrix multiplication, in which in that data engineering conference talk I went a bit deeper into matrix multiplication. But there'll be a story for another day. What we're going to do is we can see if we can derive the function of a neural network from this graphical view itself. So and see how the neural network may learn. So a lot of this talk, right? A lot of the contents of this talk comes from this paper in 1992, which says multi-layer feed-forward networks non-polynomial activations can actually approximate any function. We're going to unpack this sentence. If, by the way, if anyone has any questions, just ask me, okay? And so any mistakes I made, of course, it's mine, and you know, because I think we are all pretty rusty with our mathematics. So I'll be taking this quite slowly. I'll be starting with something like what a mathematical function is, but also I'll just jump in straight to discuss what a neural network is. So a neural network is a mathematical function. And the way you think about this is how you write a neural network, okay? So sigma is what we call an activation function, but really the meat of the neural network happens at w prime x. Usually you write it as x. When you work it out in practical terms, you do it as x times w. But this wx is basically this bit of the these arrows. That's the matrix multiplication. Following so far?
Like that's just a single layer, though, right? The equation there, right? Like
that's you got it. You got it. Okay. So
okay,
there is I'm only listing one layer because I'm gonna say something very interesting, and it sounds very controversial. But when I work out the mathematics, it's not that controversial. Okay. This is a single layer neural network. So if you take the output of this and then pass it to another W and another B and another activation, then you have a multi-layer neural network. So W and B are we call them weights and biases. There's a fantastic service called weights and biases that allows you to track your experiments out there. And this is the sort of the meat of how neural networks actually learn, because this is a function, right? And this function can change. And how do you change this function? Well, you can't change your input x. X is your input. You can't change your input x, but you can change the weights and the biases. You can't change the things in black, but you can change the things in red. And so how do you change the things in red? Well, quite simply, you use something called backpropagation. And backpropagation is a fancy name for partial differentiation. Okay, so the way you do it is to first choose a cost function that says, oh, when y hat is the predicted value, is not close to your actual value y, then I'm going to put a penalty in it, right? And then that's wrong, not dy. This is not correct. This should be the cost, right? The cost. How much of the change of the cost with regards to W it is. How much of the change of cost to B. Okay, and then you update W and B with the change the cost. Does this all make sense?
Yep. Like there's a bit about the activation function in here, though, right? Like sigma, like
yes. We're not going to talk about. We're going to talk about the activation function in a bit, which is why I'm not like I'm quickly lighting the activation function.
Yeah. Okay.
But okay, it's not delta y. It should be delta c, which is the cost. So you find how much a change the change of cost is affected by the change in W. It's basic, simple high school calculus that you learn in year 8, right? And then the updates, you update after you find the differences. So we say, oh, if I change W by 0.1 in this one, then I'll change, I'll bring the cost down, you know, that sort of thing. After you do that, you update, you change W itself to be the new version of W, which according to some formula algorithm like Adam or RMS proc, that's called gradient descent. You're walking down the gradient. There are many good tutorials on the internet out there, and I'm happy to sit down with you guys on a more sort of closed form presentation of this. But this is about how much I'm going to talk about the common way that neural networks learn. All right, so we're jumping into a mathematical function. So what is a function? I left it blank here actually, and well, a function, we write Python scripts all the time. We write programs, and we write def foo, right? That's a function. But what exactly is a function in terms of mathematics? Well, a function in mathematics has a very precise meaning. It's a mapping from one value to another value, right? So one input, one output. That is a function. And of course, we can expand that and say, we can squint our eyes and say, hey, Python functions, computer programming functions, kind of look like mathematical functions. And that's why we call them functions, right? And so consider the following definition. This is how I'm going to write function definitions with the colon equals. So we say f of x is mx plus c, where m and c are free. Okay, meaning that it's some constant value that is free. It is not bound to the function. The function only takes one input x. Following so far? And so we can write it out fully. We often write a concatenation of m and x here. That's basically fully written out as m times x. This is basically yeah. Oops. Okay. So functions have types. Okay. So a function can be a real a function. This is me explaining notation, right? So to read this, you basically say this function f, right, takes a real number and returns a real number. So if you take x times m plus c, you get m times x plus c. That will return you a real number. Does that make sense? Just like in Python, your functions have types. It's the same concept. Okay? And in general, there are two types of functions, right? The discrete functions and continuous functions. And we're not going to talk about the discrete function stuff because the discrete function is what computers do. But we're going to talk about a continuous function. A continuous function basically is a function where a small change in the input causes a small change in the output. Yeah? Follow so far?
Yeah.
Cool. Now, there is a problem with continuous functions, of course, is that we assume that continuous functions are, differentiable everywhere, but they're not true. There are some special kinds of continuous functions where you cannot differentiate. You cannot perform a dy dx on it. And an example would be the Weierstrass function, and you'll hear Weierstrass again a bit later. Okay? And the issue with, like, mathematicians like to think of the world as everything is a function, right? But everything is a continuous function. And if you think about it, it kind of makes sense. There is no, when you walk in space, in a room around you, there's no, say, you're not jumping across one coordinate to a next coordinate like a chess piece. It's not a discrete sort of step. It's a sort of continuous step. If you look at a ruler, we do make discrete markings on a ruler, but really a ruler is a continuous line. So that has sort of engendered us to think that the whole world is sort of made up of continuous functions, but there are very not so nice continuous functions, right? And our goal is to actually approximate these complicated continuous functions with something simpler. And so we can think about how you want to approximate something, right? So let's say this blue line is a continuous function, right? And what do you do to approximate this? How do you approximate this? Anyone? Any ideas?
Yeah, well, like a smoothing function or a moving average sort of thing.
Yep, a moving average is actually a very good approximation function.
Or polynomial, some kind
Polynomials are good. Yes, polynomials. We're going to talk about polynomials a lot. But you can also equally draw lines.
Yeah.
You draw a straight line here. You draw a straight line, straight line, straight line. More straight lines. More straight lines you draw.
Like piecewise straight line.
Yes, piecewise linear functions. If x is equals to 1, then we draw this mx plus m0 x plus c0. If x equals to 2, then you draw many piecewise linear lines. But if you don't want to draw a straight line, no problems. We can draw a curved line, which we call polynomials, right? Or you can use a neural network. Okay. Now, neural networks are universal approximators. Okay, it means it can approximate any function. And the controversial thing that I'm going to say is that a single layer feed-forward neural network with particular kinds of activation functions can approximate any continuous function. That is to say, your huge transformer, your huge ChatGPT, the transformers inside, well, ChatGPT is made of 3 or 4 different neural networks, but each individual neural network can be replaced by a single one-layer feed-forward neural network, and it will still work. Okay?
Yeah,
but
I'm going to doubt on that one, but I'm willing to be shown otherwise.
okay. So yes. So neural networks are universal approximators. And guess what? They're not even the only universal approximators. Polynomials are also universal approximators. And there's a very fancy proof called the Stone-Weierstrass theorem, written in 1937. This slide is in there to make me look smart. You don't have to worry about this. Right? But the point I'm trying to make is that polynomials are universal approximators. Okay? But piecewise linear functions are also universal approximators. So what is it that makes neural networks so special? The thing about neural networks that make it so special is that neural networks are generalizable. So if you think about piecewise linear functions, right, you have to write the if-then statements. There will be if-then statements that are not covered by your statements. So it's not generalizable to cases outside of it. But for neural networks, for what we can see so far, it is able to generalize well outside the domain. But again, I've even talked about generalization of neural networks. So it's not, it's a very subtle issue. It's not so clear cut that it's actually able to, just generalize. Anyway, it generalizes within its topology. Point is that, right? So okay, what makes the neural network so special, right? Now let's talk about the notation a bit. Here we see all sorts of mixed notations. Some are capital letters, some are, these are not very nice. So firstly, this is in matrix notation. So this means that this function of f is, it takes a n-dimensional vector of real numbers and then returns a m-dimensional vector of real numbers. Okay? So we can fix that. And we say, okay, we take only sort of scalar values. Okay, and then we go here. So we fix the notation, and now we look at how we represent these things graphically. So this is a neural network. So to compute this, you take x times w1 plus b, and then to compute this. So this is not the same neural network drawing as the one you saw earlier, because b is usually not drawn, but b is actually quite important. Biases are quite important, as you will see later. I'm not sure if I actually put it in the slides. But you can see that you've got 1, 2, 3, weight 1, weight 2, weight 3, and basically it's a vector, right? So if you take this multiplied by this, you get this. Does that make sense? You take one value, 1x, you multiply by 3 of them, you get that. Okay? Follow so far?
Yeah.
So
yep.
Over here, I've got only one layer, right? So that's up to the point of computing this one. And then you can also, like what Dane says, you can compute a second layer. You can do a second one. And then sum it all up. Okay. A polynomial can be represented like this. Okay. Don't worry about it. But one thing I want you to note is that I'm representing it graphically with a particular rule. Well, by the way, this is left as homework to you guys. But what I'm trying to say is that there's a particular rule that I'm using to draw these things, and the rule is vertices, the nodes, right, They represent summation and the application of a function thereafter. So it's a composition of summation, and then you apply a activation function. Or if I don't say an activation function, then we assume that an identity function is used. You guys know what an identity function is, right? An identity function is basically something that returns itself. So if you give the identity function 1, it will return 1. If you give the identity function foo, it will return foo. So there's basically no effect. Okay, but the rule is that edges represent multiplication. So x1 times x is x squared. X squared times x is x cubed. x1 times a1 is a1 x1. Following so far?
So like there's a b on this one too, right? Like the x0.
No, so polynomials have no b's. There's no biases.
Well, there's like an x0.
Oh yeah, there's an x0. Yes, that's correct. I didn't draw that. Yeah, there should be one more sort of blue one over here that connects directly to this one, to the pink one. You're absolutely correct, Dane. Right? Moving on.
Can I just ask why there are edges connecting the x's?
Because a polynomial is x to the power of 0, x to the power of 1, x to the power of 2, right? So you just times x times x times x infinity.
Yeah.
So having said this, having applied the rules, can we make polynomials look a bit better? Well, here is an example of an alternate representation of the polynomial. So you turn this, having the individual multiplications here, and you stuff the individual multiplication inside G1, G2, and G3, right? So you can define for each node you have individual activation functions. Does that make sense?
So G3 means it's a third order polynomial? Or
Yeah.
Okay.
Right. And this is if you bring this forwards, you will come to something called homograph, and the properties of functions that are important. The homograph Arnold, for example, which is what we talked about the last time. Like this new fancy neural network thing that's going on is the homograph Arnold network. There are some requirements of what type of continuous functions can actually be approximated by universal approximators, right? They have to be Lipschitz, and sorry, they have to be non-Lipschitz, and they have to be K, or one or the other. That's a whole other topic. So let's talk about activation functions, right? Activation functions are just functions, and they can be anything, right? Most anything. They, well, most anything. So this is the thing I'm trying to say, is that you only need a one-layer neural network to approximate anything, with the caveat, of course, that your activation function is not a polynomial. Because if your neural network's activation function is a polynomial, then you can only approximate up to the polynomial of degree p. Okay, that's
So
the
like
claim.
that example.
Sorry.
So like that example you just showed, like back a slide, that has a polynomial activation function, right?
Yep.
Yeah. Okay.
This is your absolute okay. You okay? Fine. You already got you got that point. That was, you caught on to the point very quickly. Very good.
Should I be quiet?
No. This is good. This is good. This allows me to move on. So the claim is this, right? You only need a one-layer neural network, and so let's see if we can do that. We are going on a journey, right? We want to approximate x with one-layer neural network where x is a monomial, and then the next step, we'll make x a polynomial. We approximate the polynomial because we claim earlier that all polynomials are universal approximators. So if you can approximate a polynomial, therefore you can also approximate anything. Does that make sense? So my claim again is that polynomials are universal approximators. And this was known in 1937. So if we want to make the claim that a single one-layer neural network can, in fact, approximate any continuous function, all you got to do is show that a neural network can approximate a polynomial, a multivariate continuous function. So we start with a monomial first, and then we make it a polynomial, and then we make it a multivariate variable, and then we make it a multivariate continuous function. Make sense? That's the journey. So we're going to start by approximating this function. F of x is x to the power of k. It's a single monomial. I don't know why it's called a monomial, but it should be called a mononomial. So anyway, so there you go. Now, once you work through all the sort of neural equation, okay, I got that and that, you will end up with this. All right, so okay, I forgot I added these assumptions. It sort of threw me off a bit. We assume that, of course, your activation function is infinitely differentiable, and it's not a polynomial. All right. Don't worry about the notation in there. And so once you work through, like on pen and paper, you work through a neural network equation. You end up saying that in order to approximate x to the power of k, you use this, and the way you do this is you figure out how to change your how to backpropagate and find the how to approximate the derivative. And you can approximate your derivative in finer and finer and finer detail by adding more powers. So it's quite simple. A neural network can, and I'll leave this as homework to you guys, can in fact approximate x to the power of k function by doing this. And of course, k would be the how deep your neural network is. Following so far?
Something like this looks like very similar to like a Taylor expansion or something like that, right? Like,
yes, Taylor expansions are used. Yes, they are used. The other expansion is also used. But yes. Oh yes. You also have to note that B cannot be 0. Which is why in neural networks biases are important. Because if you have B equals 0, then well, you are dividing over 0. Okay? Following so far, I think I lost a bunch of people.
Sorry, what is the x to the power k? Is it an input or?
So this is the function that we want to approximate.
Okay.
Right? We're going to approximate this function using a single layer neural network.
Okay.
Okay? And so if you work through the maths, you can find out that to approximate x to the k, you just need to apply this. You apply the activation k times. K to k. Yeah. Activation k times. And then you find the partial derivatives.
Okay. Partial derivative also k times?
Yep. So this is a neural network, right?
Yeah.
This part is a neural network.
Yeah.
You just derive, you find how many times let's say you want to do 3, right? Degree 3, x to the x cube.
Yeah.
So you just differentiate 3 times.
Okay.
And you roughly find out how what the W would be. You get it?
Okay. So the bias for all the functions are assuming as same B? Or?
Yes.
Okay.
isn't this like like a k-layer neural network though? Like,
Yep, it's a single layer neural network.
but how is it different from like a k-layer neural network, where like instead of having a single layer, you have k layers? Like you said, like you apply the activation function k times.
Yep.
Like, isn't that effectively just a k-layer neural network then?
So you apply k times, so you've got 3 here, 1, 2, 3. So how deep your how wide your neural network is.
Okay. So it's the width, not the depth.
Oh,
Yeah. So depth means more layers, right? 1 layer, 2 layer, 3 layers. But you are trading depth for width. And suddenly this thing becomes, oh, okay, it's so simple. So if you've got a matrix that is a million times a million, or a whatever, however many trillion parameters the GPTs have, you can do it. You can do it in one matrix. So next step, we want to approximate the function, a simple polynomial, right? Let's just say it's a simple polynomial that is not particularly in an order, it's just k and n. So we have a neural network here that approximates k, x to the k, the same neural network that we saw earlier, right? So x to the k is basically the function earlier. We already know how to do that. Okay. So x to the n is exactly the same, right? You have the same neural network there. So now the function that you want to approximate is a1 times the approximate of x to the k, and a2 times x to the n. And so you just combine the neural networks, and then at this point you times the a1s on the red parts and a2s on the blue parts, the green parts, and you got the answer.
so just a question.
Yes.
Can k or n can be fractions? So
Yes. I'm not sure. We're just going to deal with integer. So the paper mainly deals with integer exponents.
Polynomials, so they're
okay, yeah,
natural numbers, not real numbers.
okay, yeah.
So my skills in in ticks is terrible, so I ended up drawing this terrible thing. This picture is supposed to be much nicer. And so now we can get to polynomials. So we can say we can approximate polynomials by just making it even wider. So the width of your single layer now is k plus n.
Is it always the same activation? Like, what's the activation function? I think that's what I'm like hung up on. It's like, does this work for any activation function, or is it like
Yes, it works for any activation function that is not a polynomial.
Any continuously integratable.
Yes, and infinitely differentiable.
Sorry, yeah.
So your tanh, your softmaxes, well, softmaxes don't work, but your tanh, your sigmoid functions, anything with e to the x will work. All right, so then we want to make x now. Our goal is to make x a multivariate polynomial. So to do that, we need to go to a sidebar to what a ridge function is. But I don't quite remember what I did for this. But a ridge function is a function that takes an n-dimensional real number vector and returns a single value. So average, for example, is your computing of an average function is actually a ridge function. All right. And so when you have a dot product and you apply a g. So do you know what this is, right? This is a dot product. You guys familiar with dot product?
Yep.
So you take two vectors, you cross them together, you get a scalar number out. Or you dot them together, you get scalar out.
Yep.
and then you apply the scalar. That's it. That's a ridge function. And so the claim is that I can find the claim is that I can find an A, through whatever means, that I can apply this G on, right? And the neural network is able to capture it. The neural network will be able to approximate that. Let's see. Oh no, crap. So yeah, I think I have cut off a few slides, but you have to basically squish and squash. That's your transformations. You your transform your inputs and into a form that is basically x times a, x dot a, and then you apply a ridge function on it, and you can apply the ridge function multiple times, and so now you have a multivariate neural network. So a multivariate neural network would be this, but you have more x1, x2, x3, x4, x5. You know, multiple variables. You just basically take this neural network and squish it into 1x. You then apply it over here, and then you take the x2 and squish all of these values out using ridge functions. And then, so what we can say is that the neural network's hidden layers basically approximates the ridge function, which are then, of course, you can linearly combine them into x to k. And that's the output. I'm drawing an owl here. I'm very sorry, I'm drawing an owl. And since polynomials can approximate any since polynomials can actually approximate any continuous function, then we know that now a single layer neural network can approximate any continuous function. Does that make sense at all? Well,
the X part is like
the multivariate part is just, you know, if you can do it for one variable, you can do it for many variables. If you can do it for many variables as many variables, you can absolutely do it for multivariate polynomials. So a multivariate polynomial is this, right? And we can write this in form of this. Does that make sense? It's basically a vector of A multiplied by a dot crossed with a vector of x's with a polynomial in it. And then you power k. This, transforming this into this, oh, I can see why this is not making, okay. So this is supposed to be mathbf. So this is supposed to be bolded. So it's a vector. It's a vector A, not an x. This vector x. There should be an arrow or it should be bolded, but somehow it's not bolded.
Capital or something. Yeah.
Yeah.
okay.
So it's a vector. So all multivariate polynomials, right, can be written in xa times x a dot x to the power of k. And this looks exactly like this, right? X to k. Because a dot x is going to be a scalar. Make sense? I'm drawing an owl here, I realize that.
Yeah, that makes sense. I think the bit that like I got stuck up on is like it's x1 to the power of 0, x1 to the power of 1, x1 to the power of 2, da 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 da.
Yep.
X.
Then
Well,
x2 to the power of 0.
Yeah, then x2. Yeah.
And then
Yeah.
dot all the way to xk to the power of k. Or xn, yeah. Xn, sorry, yeah. Xn to the power of k.
So the
Right,
so if x is a big x is a vector, so it will be k would be common for all, right, to the power k. So it
Yep.
would be applying for x1 to the power k, x
So
a0 x1 to the power k, right? Something like that. I feel
So-
like the first one a0.
Yep.
x1 to the power k, right? It looks like if we put it that way.
Sorry.
It looks like if we put the k as the notation below, so
Yep.
wouldn't that be like a0 x1 to the power k?
A0 to, no, it's AK to the power of XK.
Okay. Okay, yeah, it's clear for me.
So we can, I assert that this statement can be written as this. And because you can write it as this, you can actually go back here and say, hey, guess what? We already know how to solve this.
Yeah.
Right?
Yeah.
And okay. So when the so what we say is that neural networks hidden layers actually approximate the ridge function, which then you are linearly combining them up like that. Like this. Basically, you form a very stupid little wide neural network. And so because polynomials, the multivariate polynomials are universal approximators, because we can approximate that universal approximator, so we are ourselves a universal approximators. Ta-da! Sorry, that was, yeah. Like I said, that's the end, and it feels like I'm just drawing an owl, especially towards the end. I think I lost a few people. Any questions?
I'm still a bit like confused on the a dot x to the power of k.
This one?
Mm,
Is there a bonus or extra summation sign in there, or are you actually doing this over every?
You're doing it over every term.
Okay, so that's not okay.
like if a is just, you know, two order, like a0, a1, and x is like two order, x0 and x1, then a dot x is a naught x naught plus a1 x1, and then to the power of k, right? That's like a naught squared x naught squared plus a naught a1 x naught x1, like two of them.
Sorry, can you say that again? I'm trying to write that down actually.
Yeah, like if you just do like a two order, right? Like,
yep.
If a is a naught a1, and x is x naught x1.
Yep.
Then a dot x is a naught x naught plus a1 x1.
Sorry, my thing just started up.
Oh yeah.
You know what? Paper doesn't need to be started up. I just cannot find a pen around me. I have a bunch of papers. Let's try this again with the actual pen and paper. Oh, an envelope and a pen. So if let's do the power of two, right? So a naught x 1 naught a1 x1 1 plus a1 a2 x1 2. Okay, and a naught x 2 0 a1 x 2 1 a2 this much that sense.
Yeah.
Right.
That was a bit blurry actually at the end there.
Okay, so we can gather the like terms of x's, becomes a vector of x once, x2, and you got a1, a2. I don't know why I can't focus.
Maybe we do this in the board next week, but we're only in office.
Yeah.
Yeah.
I'll do it on a whiteboard. But yeah, the point is, I assert that this can be written like that. And
If you get, like, don't you get like an a naught a1 times x naught x1, like sort of thing, like from doing the power of?
I see. Okay. So yeah. Okay. Okay. Yeah.
You get more
I guess-
mixing than just like you don't just have A noughts and X noughts. Yeah, like
Yeah.
this.
You're absolutely right.
The power of K is it's not that sum that you had before, right? Because there's like
Yes. Okay.
There's
I can
more
see why this is
mixing.
confusing.
but
know what?
it's the
I should-
sum of that. No, but it's not. That doesn't matter. Oh, but it's the sum of.
Let me
that.
look at my Let me look at my. So the issue is that this. I think this is the mathbf. Sum of x.
Like, isn't that already the sum, or is it the sum of that infinite sum? Of like, not
So
infinite,
this
like
is a
that
sum of an infinite sum. Not an infinite. Not
Yeah,
an
sorry,
infinite sum,
not
but
infinite.
sum of this, right? For each n less than k.
Yeah, I don't know. But there's still
Okay.
going to be like an A. Like, if you go to that next slide, I like the next slide where you just had like this one here, right? Like, if we just ignore everything past like A2, right? So we do
Yep.
A naught, X naught, A1, X1 to the power of like 2.
Mhm.
So we just write that down again, right? And we get A naught squared, X naught squared.
Yep.
Plus, and then like the last term, A1 squared plus X1 squared.
Ah,
Plus
yes.
2 A naught, A1, X naught, X1. The bomb, whatever that's called again. Yeah.
Okay, this slide is not quite right. I think.
No, but I agree with this slide. I don't agree with the last one.
Okay, those two slides, I did it like we were supposed to. I was supposed to present this last meeting, right? So, it was like written 10 minutes before the meeting. So,
Yeah.
and I've not actually gone back to this slide. So, I definitely, I will have to rework these slides.
In that previous slide, I think there's more mixing. There's like there's A noughts times A1s. There's what do they call it? Like the Pascal's triangle thing, right? Of like how you expand it all out. There's like there's gonna be like every term mixing with every other term, like
Yep.
up to K times.
Yep. Yeah, I'll rework these two slides and I'll send the updated versions to you guys. I'm very sorry for that. And maybe I'll add a couple of explanations. Right now, I think I'm getting, the point I'm trying to say is that if we can approximate this, we can approximate, because this looks like this, we can therefore approximate the fanciest shit.
It's a very nice L.
Yes. All right, so that's my talk, I guess.